Okay, so I'm kind of going to give away the excitement today. Well, I don't know if you call this excitement. But anyway, so we have this nice setup. This is an inclined slope, and we have these things that can roll, and they're supposed to, well, they could be the same mass. They're not actually the same mass, but they are the same radius. And when we put one of these on, instead of sliding down, it rolls without slipping. So this is a new condition that we're going to talk about, this roll without slipping condition. So it's a little bit, rolling without slipping is kind of subtle because if there's no friction, things just slip, right? But once it's rolling without slipping, there's no sliding, and so there isn't any friction. So you need the friction to set up the condition. But once it's rolling, then there's very little friction. So so it's kind of a funny, well, physically, we call this a constraint. So once it's obeying the rolling without slipping condition, then there's a relationship between the angular momentum in the spinning, in the rolling thing, and the speed that it's going, right? So, you know, if it's touching and there's never slipping, then the speed of the center of mass is related to how fast it's spinning. And so last lecture I talked about how much kinetic energy goes into rotation depends on the distribution of mass as a function of radius from the center of mass position. And that's that we fold into a number called the moment of inertia. So we were integrating up moments of inertia around particular spin axes. So this thing has a big moment of inertia because all the mass is as far away from the center as it could be. And so when this thing starts spinning or starts rolling, there's a lot of kinetic energy into the rotation. But if you have something else, so this is a different, this one, it's wood, the center has a bit of copper in it. So the mass is concentrated in the center. And when this thing is rolling, there's not as much kinetic energy in the spin because more of the mass is concentrated. And so the idea is that you start them up at the top of the incline, and that gives them some potential energy. And they roll down together, and one of them gets to the bottom first. So which one do you think is going to get to the bottom first? Anybody want to make a guess? The hoop or the disc with the piece of copper in it? Come on, somebody be brave. Which one's gonna win? It's like a race, yes?
The hoop.
Oh, okay, we have one for the hoop. Okay, well, okay, so now we have one for each, so now we'll try it. So I need to try and start them off together. So, just in case you think I didn't start them off fairly, let's do it again. Just to make sure I have them kind of fair. So I think even with the unevenness with how I started it, this one wins. So you win and you lose. So yeah, but why? So one person, this is easy, right? You always wait in the class and try and get people to disagree. So why? Yeah.
Because the moment of inertia for the disc is lower.
Right. So they
more mass in the center.
They both had the same amount of kinetic energy per unit mass. So they aren't actually the same mass, but it shouldn't matter because the potential energy and the kinetic energy both scale with mass the same way. So what happens when you put when the thing gets to the bottom, it has kinetic energy. There are two terms in the kinetic energy. One is the center of mass kinetic energy, and one is the rotational kinetic energy. So so at the bottom, and they're related because of this rolling without slip condition. So the rotational speed depends on the speed of the center of mass. And so this one has much less rotational kinetic energy at the same speed than this one because of the difference in the moments of inertia. So yeah, so your explanation is correct. So we'll solve that with some, we'll show that today by computing the moments of inertia for some objects, and then trying to predict what the velocity is when you give it a certain amount of energy. So yeah, so this is potential energy, which is just mg h, where h is how much height you've got, and then you turn that into kinetic energy, which is a sum of the center mass motion plus the rotational term, and those two are related because of the rolling without slip condition on these. So we have a few more disks, we might as well play around with them. So this one is a uniform density. So this one should also win over the hoop. But let's do this. So this one is the center one, and this is the uniform density disk. And we know, we're going to guess that this one is going to win because it's got more mass in the center. Again, they're the same radius, so the radius is relevant here. And so we'll see, I'll try to get them to start exactly together. So this one wins again. And so this is a trickier example. So these are both uniform density disks. So they should actually, well, and this one's wood. So they should actually reach the bottom at the same time. So let's see. I don't know, not too different actually. Not actually that different. So yeah, so you got to be a little bit careful with wood actually, because I don't know if anybody ever make musical instruments, but wood actually has quite a bit of variation in its density. So copper probably doesn't, because I think it's copper, brass, something like that, probably brass. Yeah, so if you make a xylophone out of wood or a marimba out of wood when you're hitting it, you'll notice actually if you get different grains and different densities in the wood, the pitch will vary. So if you're building something where the vibration, where it depends on the vibrational properties of the wood, you have to do quite a bit of adjustment with wood. And of course, like famous violin makers did that on purpose, right? So there's all these stories about Stradivarius putting sand on the violin to try and file it so that it had these nice acoustic properties. And the other thing that's, so wood is not always uniform density. So that could be something like that. So, okay, so we have another one. This one is a wooden disc, and it has a heavier rim, so there's a metal rim. So we can say, compare that one to the wood disc. And this one should lose, right? Because it's got more mass along the rim. So let's get this one out of the way. Yes, that one did win. So that's the hoop race, and I think we've tried them all. This one, I don't know if you guys remember, this is the one where you can get it to roll uphill. Well, you can get it to roll uphill. There we go. There it goes uphill. So can I get this one to roll down? Yeah, kind of. And it's over. Okay. So that one would be tricky to try and race with the other one because it's uneven. And not necessarily surprised when you think about it, because for these, they all have this spherical, they all have this circular symmetry, so the center mass is not going up and down. This one, the center mass is going up and down while it's rotating. You could try and predict that. It would be a harder problem to predict because there would be an oscillation in the rotation rates, and so that's harder to solve. Okay, so that's and we may get time to go talk about some of these other demonstrations. So we'll see where we get. Okay, so there's one problem we didn't quite finish last time, and I also had a question. So let me remind you what we were doing. So what we were doing was we were calculating moments of inertia. So computing. So one of the examples we did was a rod. So let's remind ourselves. So the rod, the mass, make myself right large. So the mass of the rod was a linear mass density times the length. Yeah, but our formula for the moment of inertia about some rotation axis was dv rho times r squared, where that is the distance from the rotation axis. So, the question I had involved what happens to, this is a rotation, this is a volume element, right? So it's dx, dy, dz in Cartesian coordinates. And the question I had was what happens, and we had put the x-axis here, what happens to the dy and the dz when we're doing the integral? And so I just wanted to mention that. So we've described the mass density as a linear mass density. Rather than a mass per unit volume. And so really what we're assuming is that the height here, dy or dc, whichever direction, is really small. And when you integrate over dy and dz there, so this is x, so I could put axes dy and dz here. Only one of them is out in the plane, you can do it that way. One of them is up and one of them is out. And I'm assuming those are really small, so that when I integrate over those, it doesn't really affect this distance and integrate. So how would we do that? So if I have a rho and I integrate over dy and dz, I get the mass density per unit length. So that I have a question on that. We'll try to make that a little bit clearer. So we just integrated out these other dimensions, and then all you have to do is integrate this up in x. And so what we did last time is we replaced this with dx lambda x squared, like that. And then we, for the rod rotating around the midpoint, went from minus L over 2 to L over 2, and for the rod rotating about its endpoint, it went from 0 to L. And so that's how we can solve that. So, okay. So let's move on to the last example. Moment of inertia. So this was the last example of calculating the moment of inertia. And so we had an M1 and an M2, which they're not the same necessarily. And then there's a distance between the two masses, D. And so you guys, we did vibrational molecules, the vibration degree of freedom. But when we talk about rigid bodies, they're rigid bodies, so that they can rotate. So, so we're assuming here that D is fixed now, that we're not letting it vibrate. But it could be rotating, and so if it's a free molecule, then you can describe the motion. You can describe the motion as a drift in the center of mass plus a rotation. So, so the interesting axis to compute the moment of inertia is about the center of mass if it's a free molecule floating through space. So let's make sure we make it free. So actually, this is got an axis of symmetry. So if I put, this direction x, let's call that direction x. Then the rotation axis I'll put here at the center of mass. But that can either be y or z. Well, what if it's rotating around the x-axis? What's the moment of inertia? So supposing these are point masses, then it's rotating around the x-axis. What's the moment of inertia? Anybody want to guess? What's the moment of inertia of a point mass around its center? It's mr squared, and r is 0. Okay, so what's the moment of inertia around the x-axis if they're point masses? Yes. Yes, it's 0. So, so molecules, like these diatomic molecules, have two interesting possible axes that they can rotate around that are interesting. Essentially, kind of all rotation axes in this plane. In this direction, it's dull because you don't get any energy out of it. You can't put any rotational energy in that direction. If they're point masses in a classical setting, right? Okay, so let's figure out what the moment of inertia. So I'm going to put the rotation axis in perpendicular to the axis that the molecules are on. So so instead of an integration, we've got 2 point masses. So it's easier for us to just sum m1 r1 squared plus m2 r2 squared, right? But r1 and r2 are distances from the center of mass. So that's going to be the answer. So it's just like one of the problems we did last week on center of mass, computing center of mass. So, so we just need to figure out what the distance of this guy from the center of mass is and that guy from the center of mass. So, yeah, so let's go into a coordinate frame where the origin is at the center of mass. And I'll put, so this will be the origin right here. And this x, the x-axis is in this direction. So if the origin is there, then the center of mass coordinate is 0. So x center of mass is equal to m1 x1 plus m2 x2. And r1 is really going to be the absolute value of x1. And this is equal to 0. So, so this is one of these problems where I can add and subtract things. So supposing I add m2x1 minus m2x1, then I can rewrite this. So I have m1, so m2x2. How do I rewrite this? Oh yeah, x1 times m1 minus m2 and plus m2 times x1 plus x2 is equal to 0. So I have, is that right? M1, let's see, so I wanted to do this way, m1 plus m2 plus m2 x2 minus x1 is what I want. Okay, that's good. And now this gives me x1. So x1 is now m2 over m1 plus m2 with a minus sign because I move the other side. And then x2 minus x1 is the distance in between. So this gives me a formula for this distance. And I can do the same trick to figure out what x2 is, or I can say x2 minus x1 is d, and then figure out what x2 is. And so we can figure out what x2 is, and it's d m1 over m1 plus m2 with the opposite sign. And that makes sense by symmetry. Okay, so now we take these two things and stick them in here. When we solve for I, so it's m1, m2 squared. I'll just use m for shorthand for the sum of the masses. So I need to square both of these. And then there's a d squared plus and so now I'll plug that m2, and now I have to have m1 squared over m squared d squared. So we can rewrite this as m1 m2 over m. I'm going to take one of those m's out, and then there's an m1 left, and an there's an m2 left here and m1 left there. That cancels out one of these m's, so this goes away, and then we get d squared. And then if you recognize that, does anybody recognize what that is again? Reduced mass. Yeah, you guys are getting used to that. But because it's a two-body problem, you get the reduced mass again. So mu is m1 m2 over m1 plus m2. So the moment of inertia of a diatomic molecule about its center of mass for rotation axis, it's perpendicular to the axis of the molecule, is mu d squared, where mu is the reduced mass and d is the distance between the molecules. So, so that's relevant for spectra of molecules, actually. So molecules that are in free space have rotational degrees of freedom, and their rotational degrees of freedom are quantized just the same way as vibrational degrees of freedom. So we talked about this a little bit when we were talking about quantization of energy, but you can quantize rotational energy also. And then when you do that, the relevant thing is for a diatomic molecule is the reduced mass and the average distance between the two atoms. So those are for rotational transitions. So to order of magnitude, you can figure out what that energy is. And later on, when we start talking about thermal, thermal energy, you'll see the transitions when the energy associated with rotation matches kT, where k is the Boltzmann constant of temperature, and T is the temperature. So, and then, the actual transitions will be units of h bar times the rotational energy, rotation degree with the moment of inertia, combined to give you an energy. So this is not an energy, that's just you need a rotation rate also, so I omega squared over 2 is the energy. Okay, so that was that example. So let's now move on. Okay, we got for it. It's not even that dirty. Okay, so next topic is rolling without slip. Okay. So, so we're gonna talk about things that are just like the hoops here. So this thing, and I'll put it out here so you guys can see. Actually, look at that, I have a prop. Okay, so here's my hoop, and mark a point. And now we'll mark a point of it, and we're going to assume that it's now rolling, but we're not going to let the bottom. So, so if I move this, then how far does it get? So I can mark this. This will start to go like that, and rotate it like this. Then eventually it gets so it's like this. And then we'll just let it keep rotating until it's back to where it started. So this distance is 2 pi r. That's how far it went, because the circumference of this point went up and then all the way down. So, and we didn't allow it to slip, so every point of the hoop touched the ground. And so we had to go the circumference of the hoop in order to get that distance. So, so in the time it takes to go, so how long does it take to go 2 pi r? So let's give it a time. So and let's give it a velocity. So we have a center of mass velocity times the time, which I'll just call t, is equal to 2 pi r. So let's say how long it took to go that distance. But that time is also the rotation period. So it's how long it took to do a single rotation, because we started with this point down and we got back to this point down. So, so t is also equal to 2 pi over omega. Right? So, so I can put in, get rid of this t thing. So let's do that. B center mass times 2 pi over omega is equal to 2 pi r. And so these 2 pi's go away, and center of mass velocity is equal to omega. So let's be a little bit more specific about what all these things are. So V, that's the center of mass velocity. That's this thing, V center mass. This is the radius. T is the time it took the center of mass to go 2 pi r, but it's also the spin period. So it's how long it took to do a single revolution or a single rotation. And omega is the angular rotation rate. So it's also theta dot. Okay. And this, the velocity of the center of mass is equal to omega times r. That's the rolling without slip condition. And it's nice to call it a constraint. It's a constraint. So whenever somebody says roll without slip, you immediately know this is true. And if you can figure out the center of mass velocity, you also know the spin rate. They're just related by the radius. So let's, check the units for a second. So velocity is mass per unit length. This is units of 1 over time. That's a unit of length. So the velocity is always some angular rotation rate times the distance. So if you needed to remember what it is, there's not a lot of possibilities with what the rolling without slip condition can be. These are the three things that you need to relate. So that's it, roll without slip condition. So now let's apply it to a bunch of things. So let me get that back up. Things before we get to apply it, a few more steps. Okay, so yeah.
Is that constraint only for a disk or for any circle?
Yeah, well, so if it's any circle, anything with a circle, yeah, but it's a lot more complicated if you have non-lopsided bodies. So if you have a lopsided body, then R might be changing. That's it. So yeah, so that would be harder. There is a constraint though. I mean, you can definitely think about, so like that one with the lopsided center mass, there is a constraint that friction is not allowing it to slide. And you could, that's round with the center mass off, but what if you had an oval? I mean, there is a constraint, and the constraint, if friction doesn't let it slip. So I keep using the word constraint, it has a specific meaning. It's a function that relates the coordinates, but it's not velocity dependent, and so no energy is removed from the system. And so these things have special names in the field of robotics. They're called holonomic constraints, and you've got them as dimension curved surfaces for the motion in phase space to move. So you could think about it that way. It's not necessarily easy, analytically easy to do that, but you can. You can make up a constraint for problems like that. So before I apply this, I have a couple more steps. So first I want to talk about translational and rotational kinetic energy. So a couple lectures ago, we talked about kinetic energy for a whole bunch of, a collection of particles. So, and we showed, so this is kinetic energy. So we showed that you could always take a collection of particles and write the kinetic energy like this. Actually, we need to do a sum. Okay, so this is what we call the translational kinetic energy, which is the motion of the center of mass. And this is the motion with respect to the center of mass. So if we're talking about a rigid body, then the radii with respect to the center of mass can't change. So the only thing that you can do is move in a tangential velocity direction. So these are, in fact, the tangential velocities using the center of mass as a pivot point. And so this thing is an integral over mass times radius squared times the angular rotation rate. And so this, so let's rewrite it. 1/2 I omega squared, where this is computed for an axis that goes through the center of mass. So let's be kind of specific about that. That's the center of mass, and so we're not being all that careful about multi-dimensions of spin. So we're kind of assuming that the spin axis is going to be perpendicular to the direction of motion here. But a more general formula, we have this as a matrix, actually. So, and it would be I omega dot I matrix omega. So you can generalize this to 3 dimensions of spin if you want to, and you will when you take classical mechanics. Physics 235. So I is computed, I is the moment of inertia, computed with the origin at the center of mass. So let's go back to our rolling disk. So, and think about what that actually means. So what it means is, so I can take a motion and think about the center of mass moving. So the center of mass here, I've got this hoop here, so I'll do a bunch of different positions on the rim. So that's the center, this is the translation. And this is V center of mass. And then we have the rotation. So if it's roll without slip, the bottom isn't moving. So that's exactly opposite that. And if that means the top has to be moving faster, so it's actually twice as big. Well, the final motion is twice as big, but the rotation is the same. So it's going to be vectors the same as that. Let's put things on that. This is the rotation. And we add these together. And we get the rolling condition. So I'm going to add all these vectors now. This one is not moving. Try to make this okay. That one is like twice as big. Then this one and this, I can add those together, so it's like that. And then this one I have to add this way. So I do these like that. And then this one is kind of intermediate. So, think about a wheel turning, the velocities are smaller at the bottom, the top is moving more. And so this is actually what the hoop is doing when it's rolling without slipping on the ground. But you can always do this. You can always say, I'm going to take every velocity and write it as a sum of velocity minus the center of mass velocity. So if I take the rotation and I add in this, I get that. So that's kind of the point I wanted to. So now, this is the kinetic energy. Now we're ready to start applying the roll without slipping condition. So let's do that. Okay, so the problem we're going to do is actually that demonstration. So we're going to have, hoops and cylinders of various types. And they're rolling down an inclined plane. So the problem is this. We start something up here, and this is a distance h, and it's going to roll down, and then we're going to look at the velocity when it gets down to the bottom. So the gravitational energy is, so at the beginning we start the hoops not moving, and so there's no kinetic energy. So the total energy is kinetic energy plus potential energy. So the initial energy is just the potential energy, which is going to mgh. So we're the mass. Yeah. So that's the initial energy. The final energy, which has to be the same as the initial energy, which is subtle, right? Because we need friction to give us the roll without slip condition, but friction's not actually removing any energy. So when we say the initial energy is equal to the final energy, we're assuming no energy is lost. In reality, there has to be a little bit of energy, otherwise it's lost. Otherwise, you couldn't maintain the roll without slip condition. So this jump is actually somewhat subtle. But so the final energy, if we take z to be 0 here, then there's no potential energy. So the final energy is just the kinetic energy. So the final energy is the center of mass velocity, the translation of kinetic energy. So it's the mass times the center of mass velocity squared, plus the rotational kinetic energy, which looks like that. And we set those to be equal. So the roll without slip condition, which I probably erased, but omega is V center of mass divided by r. So I can rewrite this. And it would be center of mass squared plus 1/2 I V center of mass squared divided by r squared. That. And it might be nice to rewrite this a little bit more cleanly. 1 plus I over m r squared. Okay. So given, and we can, so let's, we can cancel these m's off if we want to, but given h, we can solve for the velocity of the center of mass. And all it depends on is the moment of inertia matrix, or moment of inertia divided by mr squared. So for our different hoops and disks and things, all we need to do is calculate this number, and then we'll be able to know which one has the highest velocity. And so you can kind of get the feeling for how this is going to work. So if this number is bigger, then this velocity has to be smaller. So things with bigger moments of inertia have to have lower velocities. And that we kind of saw because this hoop was winning the races, right? So it got down to the bottom first. So, and that's because this was the largest work. Okay, so yeah, so I guess we can solve for the v squared, I suppose. But yeah, so I guess what else did I want to do? Yes. Oh yeah, so there's one last thing to do for this. So I mean, this is straightforward. If you know, if you have a roll without slip condition, what would hypothetically happen? So we've done various round things, but we can also think about, yeah. So the hoop wins, and the disc, but yeah, the hoop loses. That's what I mean. The hoop loses because it has the biggest. So we can put the hoop at the top, and then we can put a disc here, and then we can put something with a concentrated mass. Where's a sphere? Where would a sphere work be in this? Does anybody want to make a guess? For a race, we didn't do a sphere here, but let's compare a sphere versus a cylinder. Anybody want to guess which one would win? Yeah?
Sphere.
Yeah. So why?
Because it has like that mass towards the other.
Yeah, you count the mass towards the set on either side. So this one wins. Okay, what about a box with no friction? So I'm just going to put a box. So we'll put the sphere on here. What about a box? It's just sliding, no friction. Would it win or lose with the comparison to any of these discs? Yeah?
The box would win,
Yes. Why?
because it's got no energy and rotation.
Exactly, right. So all the potential energy goes into the kinetic energy, so it has to have the fastest one. So it's like you just remove this term. There is nothing here. And then this has got to be the maximum possible. So yes, that's exactly right. So that was that last bit. So the box, I did draw the box at the bottom. The box wins. So here's the box. No friction, no spin. Okay, so that's that particular example. So let's do one more rolling without slipping thing. So the next example we're going to do is this roller coaster loop example. But you're actually on a roller coaster, most of it's not spinning. I guess you could be in a cart that's spinning, but. So here's the example. We have a empty ground, and we have a roller coaster. And this is the radius R. That. We'll set that to the ground. And here's a height H, like that. And we start off with a ball up here, or a disc, could be either one. You let it roll down, and the question is, how high do you have to drop it? How high do you have to have the roller coaster so that it can reach the top? So the condition is the speed when it gets up here has to be large enough that the centrifugal force pushes it up against the top of the loop. So the energy that you start this from rest, we still have the same initial energy, H. So that's just the potential energy. The condition for it to not fall off or to make it over the top of the loop is that V squared over R, which is the centrifugal acceleration, has to be greater than G. So that's the initial energy. And this is the condition to make over the top of the loop. So our goal is to figure out what H we need so that this is satisfied. So really we need to figure out what the total energy is here. So the total energy there is going to be the change in the potential energy plus, well, so it's actually the potential energy at that point plus the kinetic energy at that point. So, so if I use potential energy measured from the base here, so that I use H, then the potential energy at the top of the loop is 2R, because that's the height from here, 2R times mg. So that's the potential energy, and the kinetic energy is 1/2 mv squared, or so this is the center of mass velocity, plus the rotational component, which is 1/2 pi omega squared. And so we can do the same thing that we did before, where we wrote this in terms of so where we wrote this in terms of I over mr squared. But if there's no rotation, like it's just a box, or or if it's an actual roller coaster where you're sitting on a cart and you don't really have to worry, the wheels are small maybe, so you don't have a whole lot of rotational kinetic energy, then you can just ignore this term. And now we can, so setting this equal to 8, these two equations can be used to solve for H. But we need to put this condition here. So we replace V with RG. So this turns into RG here. So we put RG here. RG. And we just set these two to be equal to that. You can solve for H and you'll know what the height is that you need to get over the loop. So let's put this back. So now if we have a moment of inertia, actually maybe we should solve it first. So let's solve it for no rolling. Let's solve it and figure out what you need. So we have 2R mg plus 1/2 mgr. And is equal to mgh. So I can cancel off all the m's on here, and I can cancel the g's, and I get 2 plus 1/2 plus 5/2 r is equal to h, and that's the answer. So no rolling solutions, 5/2. Okay, good. So let's take that up, and now we'll do the example where we've got something rolling. Okay, so if it's not rolling, the height has to be greater than 5 paths times the radius. So what if it's rolling? And we need to pick something that we know the moment of inertia of, otherwise we're not going to be able to solve the problem. So let's do a sphere. And we'll let it roll without slip. So with a sphere, I is 2/5 m r squared. Actually, I think I used little I left there. So that's the equation for the moment of inertia for a sphere. The sphere, it doesn't matter which direction you're at, it's always the same. So which direction the axis goes because of symmetry. So we have the total kinetic, the total energy is mgh, and that's going to be 2 rgm, and now we need 1/2 mv squared times 1 plus m, 1 plus I over m, little m r squared. Okay, so that, this is what we had written down before when we took the center mass kinetic energy, and then we had the rotational kinetic energy, but we used the roll without slip condition to get rid of the angular rotation rate. So we used the fact that V has to equal omega r to get rid of omega, and then we could write the total kinetic energy like this. And so if this is a sphere, so all the m's are canceling out, so let's get rid of the m's. So, and to make it over the top of the loop, this becomes gr. So I can write gh is equal to 2rg plus 1/2 gr, 1 plus, and if it's a sphere, that's 2/5. Okay. And now we can cancel the g's, and we've got h is equal to r, 2 plus 1/2, 2 plus 1/2 times 7/5. 7/5. Right? That's right. Yeah, that's right. And so this is, I need to turn that into 20 minutes. So this is 40, let's do tenths. 20 tenths plus 7 tenths, which is equal to r times 27 tenths. Yeah, let me know. Okay, so that means the sphere, roll without slip in order to get over the top of the roller coaster. The condition is and 27 tenths is, so let's compare that to our 5 paths. So when we had a non-rolling, we had h is greater than 5 paths r. So it might be nice to multiply top and bottom by 5. And you can see 27 is bigger than 25. So you need a bigger height. So you have to have a larger height for the sphere. Which we're not surprised, right? Because we know that if you have something rolling, you're losing some of your energy that goes into rotation. So it's not surprising necessarily that you need to have a bigger roller coaster to get over the top of the loop. So, and I guess the question is this significant? Like, if you guys ever go for bike rides when you have people with different size wheels? Does anybody notice that, like, when you get to the bottom of who gets to the bottom of the hill first? It really does depend on the size of your bike wheel. Does anybody ever notice that when you go biking with people? I noticed it because I have like a regular mountain bike. My husband has one of these tricycle things, and the wheels are really small. He makes it to the bottom of every hill before me. I'm actually in better shape than him, so it has nothing to do with being in shape. It really does have to do with the rotational energy that goes into your wheels. So there are situations, and I imagine the roller coasters, even with, when you do with wheels, some of them, not all of them, it's those the ones that are on have side wheels or something. Yeah, I'm not sure. Well, yeah, they probably all have wheels. No, so there is some kind of rotational kinetic energy you have to take into account in order to figure out if you can get over the top of something. Okay, we have a little bit of time, and the next topic is angular momentum conservation. So before we shift to that, anybody have questions? So let's take a step back, and what did we do? What were the tools we did? Mainly what we did is we figured out how much energy you get in rotation. And so there's a set of types of problems where you just figure out what happens at the end by taking into account the kinetic energy and rotational energy and possibly potential energy. So these are just like the problems we did a couple problem sets ago, where you use the fact that you can kind of keep track of energy in order to predict, say, a final velocity given initial conditions. Only now we've got this additional degree of freedom, which is the rotation. And so you have to take it into account with the energy. So, yeah. So that's basically what we've done so far. And the main thing that you need to calculate is this moment of inertia. So our next topic is angular momentum. So next week you guys are doing collision problems that have collisions. And in the collisions, momentum is conserved. So, and momentum gets conserved when you have only internal forces, because every force is equal and opposite. And so the total momentum of the system is conserved, so it's like a conservation law. So if forces are all between points, the forces are all radial, and R cross F is 0. And so we haven't got to R cross F, but the perpendicular component is 0. Perpendicular component is like a force, but it's not, we'll call it the torque. And so, and then once, for internal forces that are all radially between points, there will be the total torque will be 0. And that's going to give us angular momentum conservation. So that's where we're headed. Angular momentum is going to be a new thing that will be conserved for most physics problems. So in general, or systems conserve angular momentum. When you see things start to spin, there has to be something else moving in the opposite direction somewhere else. So let's define it. Angular momentum. So L, it's a vector. So it's defined as a cross product, actually. So you have to pick an origin, and then you have to radius from that origin. And then you take radius vector cross momentum vector, gives you angular momentum. So in a non-relativistic setting, this is R cross MV. individual particle mass m. So L is perpendicular to R and is perpendicular to V. And so things like circular motion are nice because a nice example of circular motion. We have R and V, and then so R cross V gives you L. So L is along the rotation axis, actually. So when you think about if I had a disk and I'm rotating around the center of the disk, then the spin axis is the axis of rotation is in this direction. And so R cross V is actually going to give me the spin axis. So, so cross products, you know, so any part that's not perpendicular goes away. So if I have R cross R, it's 0. If I have P cross P, it's 0. So the only thing that's left of the perpendicular components is those vectors here. So if I had something like this, this is the radial component goes to 0 when I compute the cross product. So that's not so hard to remember. What is kind of hard is sometimes it's confusing to get the sign right. And so, so there are various ways to try and do that. So if I use a Cartesian coordinate system like x hat, y hat, z hat, so those are unit vectors. One of them is in the positive x direction, one is in the positive y, one's in the positive z. I can draw a coordinate system, so this is x, y, z, like that. Then it's handy to just remember that things kind of go cyclically. X cross y hat is z hat. So if I have x cross y, I get z. And that's why when I wrote this, it's x cross y and z. That's how I can figure out. So if R is in the x direction and V is in the y direction, then the angular momentum is in this direction. And that's because I kind of remembered this. There's also this right hand rule thing where you put x, y, should be x, y, and z. So if you do x, y this way, oh, that's wrong. Did I get this wrong? I think that's right. X, oh, I know why. X, no, that's good. What?
I always know that you point your fingers in the direction of the first one and then curve your fingers left and then your thumb points in the direction of the third.
Ah, okay, right. So it's, I have pictures for this. You can see I tend to get this one, but let me draw the picture that you're talking about. The picture that you're talking about is you have a hand, and here's the, let's see if I can draw a hand like this. Then you have A, and then you curve your hand, so you take your hand and you put it in the A direction, and you tilt it this way, and this is B. Then the thumb gives you C, right? That's what you were saying, right? Yes. Okay, so that is the picture, except my hand drawing is not very good. Draw the hand a little bit better. And then you curve your hand. And you use the right hand to do it. And that's why it's called the right hand rule. So if I have A cross B, I get C. So the question is, did I get this wrong? A cross B. No, it looks all right. Just turn it this way. It looks all right, Patrick. Okay, good. So independent of these right hand rule things, those of you who do E&M next term are going to get much better at doing. And those of us who are not very good at using our right hands, we'll use this workaround. So X, Y, Z. So there's an order. So if I have the first one, the second one, I get the third one. And now I can flip it. Minus Y. So other way around. Let's flip it. So if I just have Y cross X, it's backwards. So the way, think about have, this is in terms of our permutation, 1, 2, 3. And here we have 2, 1, 3. So this one is flipped, it's out of order. So with permutations, you can always put the third one back to the beginning. It should give you the same thing. So let's do that. So if I z cross x, this is 3, 1, 2. That's as if I just moved the 3 to the front, so it has the same kind of permutation order. And that gives me a plus sign. And now I can flip these, x plus c hat is equal to minus y hat, and this is 1, 3, 2. And so this one is plus, minus, plus, minus. And then we can do the last one, which is, so I have x, y, I have x, z, I can do y, z, y, plus c, is equal to, so it's 2, 3, 1. Which is the same as 1, 2, 3, and now if I split them, y hat is equal to 1, 6. So with any vector, you can write it out like that. The other way to compute cross products, so just to remind you guys how you compute cross products. You can use it like a determinant form. I have a x, a y, a z. And c, I, j, k, x, a, y, a, z, x, y, z, this. And this is actually x hat, y hat, and z hat. So C looks like this. This is a determinant. This is the way that I remember it to do the calculation. So you multiply these together, so it's x hat times ay, bz minus bz by, plus now we do the y hat one. I don't know how many of you guys have wanted to do your cross products this way. So that's let's see, so I have this one, and now I do the opposite side of that one. Easy. And then there's the c term, which is ax ay minus ay dx. Okay, so that gives you, this is a general way to write out in any two vectors. These directions will help you get the signs right. And if you're very visual, you can figure out how to use the right hand rule with your hands. Something that I'm never all that good at. Okay, so that's the definition of angular momentum. So let's go back and do the circular orbit now again. So we didn't figure out what the size of it is. That's enough time to keep the angular momentum of the particle in the circular orbit. So angular momentum, we can talk about angular momentum of a spinning rigid body. We can also talk about angular momentum of a point mass in orbit. And in both settings, angular momentum is conserved. So I'm going to go back and forth between angular momentum of orbits, which is very handy for Keplerian dynamics, and angular momentum of spinning bodies. So let's go back and look at our circular orbit. So if I have my radial vector, I can write an r cosine omega t x hat plus r sine omega t y hat. And this is a coordinate system x, y, z with origin in the middle. Then my velocity vector is just the time derivative of this. Y hat. And I can compute L, this is R plus V, actually L over M. And if you do that, then the x times x's are going to go away and the y times y. So the other thing is I wrote down x hat cross y hat z, x hat cross x hat equals 0, y hat cross y hat is 0, etc. So only these terms will count. And this is sine squared, and that's cosine squared. And sine squared plus cosine squared is 1. And so what you get is omega squared r z hat. Okay, and this you can recognize this. That's not right. R squared omega. There's a single omega, but you get an r from each term. So it's r squared. Let's write this one. R squared omega. And this you should recognize as r times v theta. So the angular momentum of a particle in a circular orbit is r squared omega times m. M here. And it's constant. It doesn't ever change. It's constant. So we'll find that's true for elliptical orbits too in the gravitational setting. So I'm going to stop there and talk more about angular momentum in the next lecture. Any questions?
Oh, I'll see if I'll be able to.